Okay, hi and good day, everyone. So I give you all time to read on chapter clock. Okay, on page, you go to page 566. Okay, so what we will do, we will explore further on the clock design. Okay, so what are the important, why the clock is so important in the what we call basic design, right? So I give you time to read, beginning from section 13.4 until until end of the page 566. Okay, try to read first. I give you about 5 minutes. So okay, hopefully everyone get an idea. Okay, from this paragraph on the clock, section 13.4. Okay, so it tells you about why is clock so important. Okay, so normally clock is used in synchronous system. Okay, synchronous system. So the name sync here, you can imagine syncing is actually synchronized by a reference signal, and that reference signal is normally we use clock as a reference signal. So synchronous system use clock to synchronize the operation of the data. So the operation of the data can be arithmetic operation, logical operation, or whatever operation, including the memory-based element. Okay. So synchronous system use clock, use a clock to distinguish one step in the computation from previous or next step. So this is actually well known. We have discussed this, what we call as token. Last time we discussed as token. So the clock, will make sure that the token will not catch up each other. So we use clock. So ideally, this clock should arrive at all clock element. So all clock element here, so we have discussed about latch, latch and flip-flop. So these two are example of clock element. And even in your lab, you see in your lab, we have a chip, a die. Inside our die, we have lots of clock spine. Okay, a lot of clock spine. For example, 3 here, and then we have clocking element somewhere here. So that's actually the purpose of the clock distribution network. So it makes sure that very small clock skew happen. Okay, to make sure that the clock here, the main clock here, okay, has a delay, tolerable delay for the clock here, and also the next one. Okay, that's why it is very important, okay, to make sure that the clock is not to say free from clock skew, but reduce clock skew to make sure that the delay can be minimized. Okay, so ideally this clock should arrive at all clock elements in the system simultaneously. Okay, that's ideal. We want it to be to arrive at different location. For example, location number 1, location number 2. Okay, here the main location, for example, 0. So it arrives at the same time. Okay, for number 1 and number 2. Okay, but that's ideal. Ideal means that it's not happen in the practical. Okay, that is due to the delay. Okay, so that the system share common time reference. Okay, from location 1 and 2 and 0, they share the same time reference. Okay, this element, okay, include latches and flip-flop. See, okay, and also memories and dynamic gate. So these 4 is actually element of what we call clock element. Okay. Latches, flip-flop, and also memories and dynamic gate. So these 4 elements, what we call as clock element, which exists in our design. Okay, clock element. So in practice, the arrival time, okay, differs somewhat from one point to another. So that's in practical. So in practical, it's not arrive at the same time. It's not arrive at the same time. It has what we call clock skew. So that's the central challenge in the clock system design is to deliver the clock to all clock elements. So that's actually the main challenge, the central challenge, okay, on the chip. Okay, while finding an acceptable compromise among skew, power consumption, and metal resources, and also design effort. That's actually the key important point that we need to consider as a designer, okay, as an ASIC designer. Okay, so a system is designed to use one or more logical clocks. So for example, here we have the logical clock idealized signal with no skew. So that's actually ideal, about ideal clock. So logical ni what we call ideal clock, okay? No clock skew, no skew. Used by logic designer when describing system at hardware description language. So when we design, when we write our HDL, either Verilog or HDL, normally we assume the clock is ideal. Okay, means that there is no skew okay, in the design, in the clock. For example, a system with flip-flop requires single logical clock. Okay, usually called clock, CLK. A system using two-phase transparent latches requires 2 logical clocks. So remember the principles of the latch. It requires 2. Okay. Okay. What we call as PH1, Phi 1 and Phi 2. Okay. Unfortunately, mismatched clock network path and processing environmental variation make it impossible. This means that we have a delay in the clock. So when there is a delay, not in ideal clock, to make it multiple clock, that's seem not to be practical. Okay? And that's why most of the system you can see in the world, okay, most of them normally use one single reference clock and not multiple clock. Okay, if they use multiple clock, they will need a system or circuit to deal with delay in the what we call clock distribution networks. Okay, to make sure that phase is not changed, even it transmit throughout the chip. Okay. So unfortunately, mismatched clock network path and processing and environmental variation make it impossible. See, mention it, impossible for all clocks to arrive at the ideal time. So that's actually about practical of the clock. So designer must settle for actually receiving multitude of skew physical clocks. So that's what we call as physical clock. So compared to logical clock. Okay. So normally, physical clock is actually the actual clock lah, not the theoretical clock. Okay, so when we design using HDL, we assume the clock is a logical clock. Okay, not a physical clock. Okay, so distributing a single clock across the entire chip is in a low skew fashion. So low skew, which is good lah. Okay, low skew, which is good. We try to reduce the clock skew. It's challenging. Okay, distributing more than one is nearly impossible. So normally we use a single clock. Okay, single clock like we have here, main clock, and then distribute across the chip. Only one single clock. Okay, see here, in only one single clock distributed across all clock element in the chip. So like your lab lah. If you this your lab, you can see lah. Okay, right. So therefore, most systems distribute a single global clock. We have single global clock, even though they may need multiple logical clock. Walaupun the system need multiple logical clock, we use the single global clock, okay, instead of generating multiple logical clock. Okay, right? So local clock gators, normally they use clock gators lah. Okay, located near to the clock element, produce the physical clock and drive them to the element over short wires. So this is actually what we wanted to see in our example after this lah. Okay, example of clock gators, so we call clock gators. So example of them including buffer or inverter. Okay, like this one, buffer. Okay, AND gate. So AND gate normally we see in what we call low power system. We want to enable and disable the clock distribution to a certain area of our chip. So we use AND gate. I think we have discussed this last time. To stop the clock to unused unit. So that's what we call low power design technique. So we don't use all inside the chip. We don't use all unit inside the chip. So maybe we have our chip, for example, this is our chip. So in our chip, we have 4 portions, for example. So we have adder, we have subtractor, we have, for example, multiplier, and we have divider, for example. So maybe we want to use adder, for example, at a time. So we turn off the others by using the clock gator. So we don't supply clock to this 3 region of our chip. We only supply to this region only. So that's actually, we save a lot of power when we stop the switching. Then why we stop the clock reduce powers, and then we will talk into detail about this in under topic power. All right. Okay, so inverters to produce complementary clock. Okay, complementary inverted clock. Okay, pulse generator for pulse latches. Okay, don't worry about the last word. Okay, the term clock skew has been used informally in many ways. Okay, we define skew as a different. So this is actually the definition of clock skew. So actually a lot of definition. So you may use this as well. Okay, I will accept any other definition that closely related to the topic we discussed on the clock skew. So here is mentioned that we define skew as the difference between the nominal and actual inter-arrival time of a pair of physical clock. Okay, so this is another definition of clock skew. So in short, we discussed already last time, different in the clock arrival time. So that's the best or the simplest way to mention what is actually clock skew. Okay, and then the one highlighted here is actually more specific. So difference between the nominal and actual inter-arrival time. It's referring to arrival time of a pair of physical clock. Okay. For example, so here we have an example. I give you time to explore this example. Just focus on figure 13.18a first. Okay. You look at this example. This one. We discuss after a few minutes. I give you time to imagine and explore the explanation. So you read this part and relate to the diagram here. Try to reduce the size so you can see them together. Okay, try to relate with this. I give you a few minutes to read. Okay, welcome back. Right, so hopefully everyone has an idea, okay, about this diagram. Just focus on figure 13.18a first, huh? Okay. So here is actually the explanation. Figure 13.18a shows a system with two flip-flop. We have flip-flop 1, okay, and then flip-flop number 2. And then we have, here is actually the global or the main clock, right? And then, so these two, it's actually a clocking element, okay, a clocking element. In this case, flip-flops. Okay, flip-flop, these two flip-flop are the clocking element, right? We need to supply a clock, okay, from the main resources here, to the clocking element inside our chip, okay? And so the clock derived here from the main clock is clock 1 and also clock 2, CLK1 and CLK2. And then we have a buffer here, okay? Buffer here with delay of the buffer is 60 picosecond, the first buffer, and the second buffer is 90 picosecond. And other than that, we also have delay or wiring delay of 200 picoseconds for the wire number 1, wires for clock CLK1, and we have another delay for wires that deliver clock number 2, which is 195 picoseconds. So clearly you can see here in terms of the delay, okay, of the wires, delay for wires for clock number 1, the delay is more than the clock number 2, okay. But in terms of the total delay, you can sum them together lah. You sum up, okay, 200 plus 60, and you get 260 picosecond. That's actually the total delay for path number 1. And then here you sum up with what we call 195 with 60, which is the total delay is actually belong to this, the longest delay. Okay, the longest delay belong to this path. Okay. All right, because it's 280 plus. Okay, 280 plus 85, 285. So clearly you can see the delay here is longer than the first path. Right, so that's what I actually mentioned here. So both should receive the logical clock with 0 inter-arrival time. So you explore this first. I give you another time to explore before we continue. Right, so when you read this, so both should receive the logical clock CLK with 0 inter-arrival time. So that's actually what we call ideal case lah. So 0 inter-arrival time. Okay, but the actual received physical clock CLK1, so that's what we call a physical clock lah. Okay, so in what we call theory, okay, the clock arriving at here same as the clock here lah. So GLCK here pun GLCK lah, but that's not happen in practical, and that's why they give different name lah, CLK. 1 and CLK2. Even CLK1 and CLK2 also has different in terms of arrival time, because we can clearly see here the delay also different, and that's why we have a clock skew. And clock number 2, CLK2, because of different in the delay of the clock distribution wires. So you can see here different in the delay of the clock distribution wires. Okay, and the local clock buffer. Okay, we see here the local clock buffer here, different delays, 60, 160, 190. Okay. Okay. CLK1 arrived. CLK1 arrived 25 picosecond before CLK2. Okay, how you get it? Because this is faster compared to this, so the difference is actually 285 minus 260 lah. Okay, 260 is actually the difference is 225. So means that clock number 1 arrived earlier than clock number 2, because of the delay is shorter than clock number 2. Okay, number 2, right? Therefore, we say that the clock skew is 25, and that's how we determine the clock skew. Different in the clock arrival time, so the difference is 25. All right, that's actually the point that I want to share with you all. So if you ask how to, what is actually the clock skew, and demonstrate what is a clock skew with the aid of a diagram, you can use this kind of example, okay, to illustrate and demonstrate the clock skew and the importance of the reduced clock skew in our global clock distribution network. All right. Any question? Clear? Okay. So if clear, you can read further. Okay, I give you time to read. Okay. So from this lah, okay, from this portion, you can read until until here. Try to read first. Okay, so hopefully you get the point. So maybe I can highlight. So we give 30. Instead of 20, they give 30. Using the slower clock buffer on clock 2. So you can see here, we give a slower clock buffer here, clock 2. And that give the overall difference will give you 30. So, which is additional 5 time unit lah. On this case, 5 picosecond. That's actually what normally designer does lah, okay, to make sure that the time is actually achievable lah. What is actually our system, our design system able to compute the data without producing unwanted data or error data. So in this case, so let's read from the beginning. So sometimes designers intentionally means that purposely, by intention, okay, delay clock to solve setup and hold time problem. So they add additional 5 time unit or 5 picosecond. Instead of 25, it becomes 30. Okay. For example, suppose that a critical path existed between F1 and F2 in figure 13.1a. So F1 and F2. So the path here we have what we call critical path. Okay, between F1 and F2. Okay, the designer might intentionally delay the clock to F2 by 30 picoseconds. So clock to F2, clock from here to F2 by 30. So to give it by 30, so this will become more delay. Okay? To give more delay is actually, we give slower, we use slower local clock buffer on clock 2 on here. So here we substitute with slower clock buffer. Okay, slower clock buffer, which is additional 5 lah, so 95 lah this one, 95 picosecond. Okay, so when this become 95 picosecond, so the total delay will become 290 minus 260, and then the delay will become 30 instead of 25, 30 picosecond. So that's actually what the sentence means lah. Okay. So there we give additional delay. That's actually give us the longest path lah. Okay, remember critical path is actually the longest path in the combinational logic. Means that here will give you the longest path compared to the first one, because this give you 290 compared to 260 here. So this is actually the critical path, what we call as, we label as CP, critical path. Okay, and then the additional 5 just now we call them as a clock skew. Some designer call this 30 picosecond delay intentional skew. Okay, we prefer to call it intentional delay and reserve them as clock skew. So normally they use all of the delay as a clock skew to account for unintentional difference in the clock arrival time. So it gives 30 as a clock skew. So either you give 5 or 30, that will be acceptable because of the definition here. So clock skew can also be measured between different edges of the clock. I think this one I mentioned in the class last, I forgot last lecture lah. Okay, between different cycles, we can see here lah. Okay, different in the clock arrival time can be seen from the clock edges here. So for example, here you can see it's okay, but the other side is a bit different in terms of the edges. Okay, see the difference here and okay, here and here. Okay, all right. So you can read on your own on the explanation here. Right? So I plan to go into this, but we don't have enough time. Maybe we will continue next week. Okay, so clock system architecture. This is actually what I mentioned to you. We have we have AND gate. Okay, we can also have buffer. So buffer for what we call a clock distribution. Maybe I use different color so that you can identify the purpose of having a clock buffer and also clock gate. Clock gators, they call them as clock gators. So one used for buffering the clock to make sure that the clock has a less clock skew at the arrival destination or clock element. And we have another one that called as AND gate, used for controlling the clocking operation. Either you want to turn on or turn off the unused block of our chip. Okay, they use the AND gate. So this is what we call as low power design technique. I think they mentioned here, we can read first before we go for detail in our next lecture, maybe next week. Okay, and then from there we shall discuss about the clock distribution networks. We skip this first. We go to the clock distribution network, which we have grid type, H3 type. Okay, and then we have yeah, someone asking, wanted to ask? No? Okay, so we can explore first before we go for a lecture next week. So you can see the pattern, spine number 1, spine number 2. This is actually, you can see clearly in our lab. Okay, in our lab. Like this one, in our lab. When you do the lab, so this is actually the clock spine. Okay, that used to deliver the clock with less clock skew. We also have a hybrid version of the clock. We shall discuss later. Okay, any question before we end? Thank you. So I will stop recording first.